Okay, so today the plan is to go into Löwner chains and some complex analysis and deterministic stuff. But as yesterday, I want to start with something that is a complement to the course of yesterday. So remember, I was speaking about loop erased random walks. And in the statement of the Markov property for the reverse random walk, I told you that there was this reversibility property, which said that if you look at the Green function at x in a graph times the Green function at y in the graph minus x, this was equal to, so this and this are not the same g, maybe it's not in a domain. Now this was the same as doing this in the other direction, so g of y in omega times g of x in omega minus 1. And essentially, once you have this, you can prove that the loop erased random walk has the same, well, has the Markov property if you condition it to exit at a given point. So there's something more you can do with this, and it's a bit counterintuitive, but turns out that it will come back maybe if I have time to speak about scaling limits of these kind of objects. What you can do is the following. Take 2 points A and B in a domain and start with the random walk which is reflected on the boundary. It just means that the walk, when it's on the boundary, it is not allowed to exit the domain. So it's just a simple random walk, and you do the loop erasure until you reach point B. So in the end, you obtain some curve going from A to B. So x is a simple random walk. Tau b is the inf of n such that xn is equal to b. And you look at the loop erasure of x between 0 and tau b. So this is perfectly well defined, and that gives you some simple curve joining A and B inside the domain. And what is completely surprising if you see that the first time, so let's call this loop erased random walk from A to B. The thing is that, and a posteriori, once you have the statement, it's not completely surprising because of this exchangeability, that the loop erased random walk from A to B has the same distribution as the loop erased random walk from B to A. So the loop erased random walk is reversible in distribution. So of course, if you take the same simple random walk path and you loop erase it in both directions, you get different paths here. But in distribution, you get the same thing. And here, of course, you have to reverse time just to make the walk oriented in the right fashion. Okay, and in fact, I just want to state the result of Wilson's algorithm because that puts this in a more general framework. So here is another statement. So start with omega, which is a domain in the plane. Assume it's finite, it's bounded, and it's discretized by some lattice. So that's the same framework as usual. And then you can look at big T, which is the set of spanning trees. Spanning trees of omega. So a spanning tree of omega is just a subgraph of omega, which is spanning in the sense that it contains all the vertices. And it's a tree, so it's connected and it has no loop. So if this is omega, is something like this, maybe. So it's just a tree that goes everywhere in omega. And this is connected. Okay, so that's T is a finite set because the graph itself is finite. And you call uniform spanning tree, or UST, that's the uniform distribution on T. So you just pick a spanning tree at random out of the finitely many spanning trees that are in this graph. So that's perfectly well defined. That gives you a random graph that lives inside omega. And the fact is if T is a uniform spanning tree in omega, and if you take 2 points A and B in omega, so because T is a spanning tree, it contains both A and B, and there is a unique path between A and B inside the tree. So let's say that this is A, and this is B. Then there is a unique path doing something like this, connecting A to B inside the domain. And the fact is, this path, which we call gamma AB is distributed exactly like the loop erase random walk. So gamma AB is a loop erase random walk from A to B. So if you know that, then the reversibility is clear, because gamma AB does not depend on the ordering of A and B. You just start with a uniform spanning tree, you pick 2 points, and the path is the same from A to B and from B to A. So in particular, it will tell you that the loop erase random walk is the same in both directions. It tells you a little bit more. It tells you that there is a nice way to construct a uniform spanning tree, and that's called Wilson's algorithm. And I will just draw a picture and not put words, but that's just to finish the part about discrete models. So assume you wanted to study numerically the uniform spanning tree. You would like to sample a uniform spanning tree. So to pick a tree at random in the domain. And it turns out that there is a very nice way to do it, which is known as Wilson's algorithm. And you can do the following. So pick a point, say x0 in the domain. And this will be your starting point for the construction. And pick another point, x1. And from x1, you just construct a loop erase random walk until the underlying walk touches x0. So you look at the loop erase random walk from x1 to x0. That gives you a subgraph of omega. And two things can happen. Either it's spanning or it's not. If it's not spanning, you can pick a point in the complement, x1, x2. And from x2, you can construct a loop erase random walk until it touches what you have already. So something like this. And you just continue like this. You add x3 here, and you add a loop erase random walk to the previous constructed graph. And you continue like this until you have exhausted all the points. So as long as you are not spanning, there are new starting points available. But eventually, because omega is finite, you will end up with a spanning tree. And of course, by construction, you can never create a loop. So what you get is a spanning tree. And the proposition is that what you get is a uniform spanning tree. So what you get has uniform distribution out of all the spanning trees in this domain. Okay, and if you have time during this school, which I think is very unlikely, but who knows, because of the rain, maybe you will get bored this evening, you can try to prove this. And the proof is you just use this again. So you use this repeatedly. So what you will get is something like fix a tree, T, and look at the probability that this is the tree that you get in the construction. It just means that first the path from x1 to x0 is exactly the path in the tree. And the probability to get a given path using a loop erase random walk is something I wrote yesterday. It was a product of two kinds of terms, terms like this, and terms like 1/4. And in the end, if you write all the steps of the algorithm, you get a certain number of terms in 1/4. And the number of these is the number of bonds in the tree. But this is deterministic. Because of Euler's formula, the tree always has n-1 edges, where n is the number of vertices in the graph. And the remaining part is a product of Green functions here. But these do not depend on the order in which you proceed because of this exchangeability. So once you have this, proving that what you get does not depend on the tree is just a matter of reordering the terms. And it was pretty well. It's not very intuitive. I don't really have a grasp why this is uniform, but at least the proof is not difficult. You just use this repeatedly. Yep.
What happens if you did the same thing with self-avoiding instead of ignorance?
That's a tricky question, isn't it? So certainly it will start to depend on the order in which you choose the points. And the answer is I don't know. But I mean, here the exchangeability is really essential to prove that this is well defined.
You get a different distributed
Sure, you do, but the distribution depends on the enumeration of the vertices, I think. So it's not as universal as this one. I don't know, if somebody asked me the question, I would ask you, so. Okay, so that's the end of chapter 1. So chapter 2 will be really about SLE itself. So the question is the following. Assume that you have a discrete model, you have an interface, or you have a path, and this is defined in a domain with a mesh delta, and delta goes to 0, and you want to identify what turns out in the scaling limit as delta goes to 0. And if you remember what was the case for the loop erase random walk, so for the loop erase random walk, we obtained a few features of what the scaling limit should satisfy. So the scaling limit should be a simple curve. Simple curve. So this is not completely essential in what will follow, but it will make the pictures nicer, and I will come back to that very soon. Second thing is conformal invariance. And for the loop erase random walk, it's not completely clear why there should be conformal invariance, but I argued a little bit that it was reasonable to expect. And for percolation, it's a fact because of Smirnov's theorem that at least there is some conformal invariance in the scaling limit. And the third property was the domain Markov property. So we need some kind of structure theorem saying that if you have a random curve satisfying these properties, then it's one of a one-parameter family of random curves. Something like, so the parallel statement would be if you have a real-valued process which is Markovian and has stationary increments, then and it's continuous, then essentially what you get is Brownian motion, and there's a one parameter which is the speed at which you move. So we need something like that, but that will speak about curves in the plane instead of real-valued functions. So this is what we're aiming for, and this is what Schramm did, and that leads to the introduction of Schramm-Loeffner evolution. So keep that in mind. What we want is some kind of structure theorem for planar curves. But before we do that, we need one tool, which is essentially what I will speak about today, which is known as Loeffner chains. So somehow, it's the same kind of idea as you saw in the talks by Jean-François Legal, that you have a complicated object. It has a lot of geometry. Here it's a random curve in the plane, or it's a curve in a domain. And he had a tree. What you want to do is to encode this object using a much simpler object. So he had a tree or map. I guess very soon you will see how you can relate a map to a tree. And by the contour function, you get a path, a dig path. So it's a real-valued function in R. And so this is a simpler object than this. It's just takes the problem back to real analysis, and you have lots of tools, and you know what to do. So here the idea is the same. We will start with a curve in a domain, and the goal is to encode it, and this will be given by learner, by a path in R. So of course the method is completely different, but the main motivation is the same. You want to encode something complicated as something a little bit simpler. And in doing that, you have to forget about some information because, well, there is more information in the curve than what you will get in the path in R. So I will just rewrite what I wrote yesterday. So note. So we talk about path up to time change, up to strictly increasing time change. So really we want to identify two paths that go in the same places in the same order, but at different speeds. And that was this definition of the distance between gamma 1 and gamma 2, which was the inf for all time changes, so from 0 tau 1 to 0 tau 2, and strictly increasing, of the L infinity norm of, so which one is it? It's gamma 1 minus gamma 2 composed with phi. So that's the typical distance between paths we want to consider, and it just says that we want to identify paths that are described in different speeds. And as you will see, if you take a curve in omega but you forget about the time parameter, then, well, essentially you can see a curve as, well, two real-valued functions as the coordinates, but you can also see it as a time parameter and something else which gives you the second coordinate. And if you are clever enough, you can encode that as a real-valued function. So somehow forgetting about the time parameter will tell you that there is less information to keep track of, and that's reasonable that you can encode something as a path. So this is maybe not very convincing, so I want to just start with doing actual mathematics and give you actual statements of what happens. Okay, and then tomorrow what I will do is, once we have the theory of deterministic random Loevner chains, you will end up having a path with values in R describing the random curve. And the question is, if you have this as properties of the curve, what do you have as properties of the path in R? And can you identify it? And once you know how to do that, well, you get SLE, and then you can start moving backwards and actually derive properties of the scaling limit. Okay, so here is the framework I want to start with. So that's the unit disk. This is the origin of the unit disk. This is 1. And I want to start with, so is this the one that is white? Yes. So I want to consider something that looks like a loop erase random walk. So it's a path that goes from 0 to the boundary of the domain. And it's a simple path. But as you saw yesterday, it's nicer to look at the loop erase random walk backwards because it has the Markov property. So the framework will be, I have a simple curve gamma, like this. So this is gamma, which is a set of gamma t for t positive. It lives inside the unit disk. It doesn't touch the boundary except that gamma 0 is equal to 1. So the assumptions will be, so gamma 0 equal to 1. Gamma t is in U, which is the open unit disk. So that's the set of Z such that modulus of Z is strictly less than 1. And this is for all t positive. Gamma S is different from gamma t if S is different from t. somehow 0 is a fixed point, and I want to assume that the curve does not go through 0. So gamma s is different from 0 for all s positive or 0. And one additional requirement I will have is something that will become clear. That I want gamma t to go to 0 as t goes to infinity. So it's really something like this. You get a curve, and the curve approaches 0 as t goes to infinity. OK, that's the framework. And this, I want to call this the radial framework. And radial because, well, there is a marked point inside, and you approach it so that it's something that lives around an interior point of the domain. And in fact, when you introduce Leuven chains, there are two choices you have. You can speak about the radial case, or you can speak about the other, which is the caudal case. And so I will just draw the picture on the right, and you will see that some things are easier in one case and some things are easier in the other case. So I will try to mix them to obtain something that is as clear as possible. So here is the caudal case. Caudal case will be the case of a domain with two marked points on the boundary. And here there is one canonical domain, which is the unit disk. Here the canonical domain I will look at is the upper half plane. So this was U, and this is H. So that's the domain. There is a marked point at 0. And the other marked point on the boundary will be at infinity. So infinity is over there. And again, there will be a curve inside this domain satisfying the same kind of hypothesis. So gamma 0 will not be equal to 1. It will be equal to 0. And the curve will live inside the upper half plane. It will be a Jordan curve. It has no double point. It doesn't touch the boundary. It doesn't come back to 0. And it goes to infinity as t goes to infinity. So this is the other kind of curves that I will like to describe using a Leuven chain. So typically, this will be the case when we'll speak about the loop erase random walk. And this will be the case when we speak about percolation. If you remember what I told you about the exploration process of percolation, it was a curve starting from the boundary and exploring between two different colors and ending somewhere on the other side of the domain, but on the boundary. So this will be the topology that is relevant for percolation. And this will be called the caudal case. OK, and as I said, there are things that are easier to see in the radial case and things that are easier to see in the caudal case. So I will start with the radial case. There will be a few black boxes that I will keep because they are easier to explain in the caudal case. And once I'm done, I will fill in the holes by describing the caudal case. OK, so this is the framework. There is a disk. There is a curve inside the disk. And just to fix notation, I will denote by kt. Kt will be the path between 0 and t. So this is a shortcut notation which I will use intensively. That's just a set of gamma s for s between 0 and t. So I will denote by ut the complement of kt in the disk. So that will be the disk minus kt. OK, and because we start with a Jordan curve, if you know ut for all t, you can recover the curve itself. Gamma t is just the intersection of ut minus epsilon as epsilon goes to 0 or something like that. So this contains the whole information about the curve. It will not be the case when the curve is not simple in general, but for the moment, assume that the curve is simple because that's already something non-trivial to do. OK, so if you've been to the exercise session yesterday, you know about the Riemann mapping theorem. So here is the picture. This is 0, and I will do the picture for fixed t. So for fixed t, there is some kt like this, and ut is the complement. So if you look at ut, it's a simply connected domain, which is bounded. So by the Riemann mapping theorem, there is a conformal map, which I want to call G sub t, that maps ut to the unit disk. And in fact, there are many such maps. You can, well, if you were to the exercise session, you know that there are 3 real parameters. So you can normalize gt in a few different ways, and it turns out that the right normalization here is there is a unique gt that maps ut conformally to u, satisfying that gt of 0 is 0 and gt prime of 0 is in R plus. So G maps 0 to the origin of the plane, and it maps a tangent vector in the real direction to a tangent vector in the real direction. And so these are one complex parameter and one real parameter, so that's 3 parameters. It gives you uniqueness of the conformal map. Okay, so once again, if you know all the GTs, these give you all the information on the curve gamma. Because if you know GT, you can look at GT minus 1. You can map the disk by GT minus 1, and it will give you UT. And once you have UT, you can reconstruct the curve. So far, we just encoded a complicated object, which is a curve, in something which is even more complicated, which is a sequence of conformal maps. So we need to work a little bit more. But this is the starting point. So we are given this family of conformal maps. So the next step is the following. So remember, we want to speak about the curves up to time parameterization. We want to identify curves that are reparameterization of each other. So we might say this in another way. We want to have a natural time parameterization of a curve. So we start with gamma, and we want to parameterize it in a natural way. And natural in the sense that it will make the sequence GT, which we want to use, as nice as possible for what we want to do with it. So we want to say something about which time parameter we need to choose. So here, well, if it's the first time you think about this, it's not really clear what to do. But I want to do a picture before I tell you what the time parameter is. So assume you start with a curve, and you give 2 times, so s and t. And you want to encode the curve up to time s, and then the curve up to time s plus t. So you have this curve, which is here. And you have this picture here. Okay, maybe I will switch. So I have the curve up to time t, and then there is the future of the curve, which I will draw in yellow, like this. And this completes into kt plus s. So what do we have on the right? I will finish the picture on the right. So the map GT maps UT to the disk. What it does on the boundary is the following. So, okay, I don't want to go into the local connectivity of the boundary, but let's say that GT automatically extends to the boundary of UT. So the boundary of UT is something like this. There is the circle, and then there are the 2 sides of the curve. And what GT will do is it will cut the curve in 2, and it will spread it on the boundary. So the image of the curve itself will be some interval along the boundary. And the image of the tip, so this is gamma t, will be somewhere here. So this is gt of gamma t. Okay, and then the future of the curve, so this yellow part here will be mapped to something here. And so this is gt of gamma between t and t plus s. So then, okay, you want to continue the picture. You want to look at g sub t plus s. And, okay, it should fit here. I will remove this. So what happens if you want to describe the curve up to time t plus s? There will be a map gt plus s, which maps ut plus s to the unit disk. So here is the unit disk with 0, and there is this map here, which is gt plus s, which maps ut plus s to the boundary, well, to the inside of this disk here. And so to draw it with colors, you will find something like this, and the coloring will be like this. So that's gt plus s. But there is another way to map ut plus s to this disk. You can first use gt. You arrive somewhere here. And then this domain here is just gt of ut plus s. So it's a perfectly good, simply connected domain. There is a unique conformal map here, which I want to call g sub t and t plus s. So gt is g at time t, and gt t plus s will be g between times t and t plus s. So g is the unique conformal map mapping this domain to u and normalized in the same way, so fixing 0 and with positive derivative at 0. So it's as unique as g t plus s. And if you look at the compose map, so first gt and then g between t and t plus s, you get a conformal map between ut plus s and u, which fixes 0 and has positive derivative. The derivative at 0 of the composition is just a product. So it's still a positive number. So by uniqueness, if you normalize all the maps the same way, what you get is that gt plus s is nothing else than gt t plus s composed with gt. So it's some kind of semi-group relation that if you have gt plus s, you can split it at time t and build it by composition. Okay? So this will come back also in the causal case, and this will be the case in the causal case as well. But then, remember, we are looking for a natural time parameterization of the curve. And we want to say that if the right time parameter for this, for gamma t, is t, and for gamma t plus s, the time parameter is t plus s, we want to say that the right time parameter for this map, so the right time parameter for the yellow curve here, is still s. So if there is a natural, geometrically natural time parameter for the curve, it has to be additive somehow. It has to say that you run the process for time t, then you run the process for time s, starting at some different configuration, but it's still from time s, and what you get is what you have at time t plus s. So you want something additive, so some feature of gt satisfying that this feature of gt plus s is the sum of what it is at time t and what it is at time s. And you want it to be adapted to the geometry of the picture, so it turns out that the most natural thing to look at will be that you can look at the log of gt prime of 0. I want to call that at. So gt prime is positive, so it has a log. And again, if you have been to the exercise session, you will see that if you look at the inverse map is defined on the unit disk, and it arrives to something which is smaller than the unit disk. So by the Schwarz lemma, its derivative is smaller than 1. And strictly smaller than 1 because you strictly remove something. So the derivative of gt at 0 is not only positive, it's bigger than 1. And so the log that you get here is a positive number. And then, so if you look at this composition, gt plus s is gt composed with g between t and t plus s. Well, that fits very well because that will tell you that, so gt plus s prime of 0 is just a derivative of a composed map. So it's gt prime of 0 times gt t plus s prime of 0. And so if you take the log, what you get is that at plus s is just at plus this for gt t plus s, which I want to call a between t and t plus s. Meaning that a does behave like a time. That what you measure on at plus s is the sum of what happens at time t and what happens for time s after that. So this is the candidate for the time parameter. And so we can assume, so what can you assume? So because of Schwarz lemma, a is increasing. That's the remark I just made, that if you look at the map backwards, the derivative is less than 1, strictly less than 1. So this tells you that a is strictly increasing. This is always strictly positive by Schwarz lemma. So a is strictly increasing, and on the other hand, it's continuous, because if you remove something very small, the map is very close to identity, so the derivative is very close to 1. So a is a continuous, strictly increasing function of t. It starts at 0, because at time 0, the unique map is the identity. And so you can always assume that, in fact, at is equal to t. So either you assume it, or you just say that if you start with the curve, you construct gt, you measure at, and this gives you the natural time parameterization of the curve. So you can use at minus 1 as a time change here. And that will give you a new curve, which is identified to the first one for this distance, and which does satisfy that at is equal to t. Okay, in other words, that's equivalent to saying that gt prime of 0 is equal to exponential of t. So assuming this is just something about the way something about the speed at which the curve is drawn in the plane. And that's exactly what I was saying here, that if you start with a curve, you first choose a natural time parameter for the curve, and then the rest of the information will be much simpler to look at. So here is the black box that I will come back to when I speak about the caudal Loeffler chain. So assume that indeed at is equal to t. So step 2 will be, so step 1 was the choice of a time parameter. So time was equal to the log of gt prime of 0. Step 2 will be to look at what happens for a very small time. So what happens for t small? So here's a picture for t small. This is the disk again. This is 0. This is 1. And this is the curve for a very small time. So this is gamma at time epsilon. So you have the map G epsilon, which maps the complement of this to the unit disk. So it arrives somewhere here, and this is very small. And so this is G epsilon of gamma epsilon. But if you look at this domain, it's very close to the unit disk. You just remove something that is infinitesimally small. So G epsilon is very small. It's very close to the identity. So G epsilon is approximately equal to the identity. And as it turns out, and for the moment it will be a black box because proving that first for the caudal case will be easier. As it turns out, if you look at the difference between G epsilon and the identity, so if you look at the derivative in time of gt at time 0, then it turns out that the differential in time is well defined. That this time parameter is exactly what you need for the map to satisfy some differential equation at time 0. So again, I will write the formula. I will write the derivative at 0 of gt. And I will not tell you why it's true, because it will be clearer for the caudal case. And once you have it for the caudal case, it's not hard to come back to the radial case. So I write it as a fact. And of course, you can prove it directly in this setup, but it will be better to wait a little bit. So the fact is the following. You look at G epsilon of z minus z. You want to see that as a derivative, so you divide by epsilon. Then you let epsilon go to 0, and you see what happens. And what you get is this. So here is the proposition that the limit as epsilon goes to 0 of this ratio, should I wait? So proposition, the limit as epsilon goes to 0 of g epsilon of z minus z divided by epsilon, so the increment of g as a function of time. So this is the same as d over dt of gt of z at t equal to 0. This turns out to be equal to z times 1 plus z over 1 minus z. Okay, I won't prove that, but I will tell you why something like that is natural. So if you look at the map here, well, because this is infinitesimal and because the curve is continuous, or it's actually sufficient to look at what happens when the slit here is horizontal, when you remove something that is straight. And then if you look at the flow by gt, what you see is that, so 0 is a fixed point, so the flow is 0 here. There's no movement around 0. But around here, you have to open the slit. So the mass will move like this. It will follow gamma to the boundary. And then on the boundary, it will move away from 0 because something has to move away to make room for the image of the slit here. And here, by symmetry, the flow will be 0. So there will be a vector field somewhere like this, and the derivative in t is just following this vector field. So it has to be 0 here. So what you're looking for is a vector field in the disk that is 0 here, that is tangential along the circle, and that has some singularity at 1 that makes the map not 1-to-1, that opens the boundary. So there needs to be a pole somewhere at 1. It has to be 0 here, and it has to be tangential on the circle. And this is what happens. This makes it equal to 0 at 0. That's the pole at 1. And the 1 plus z just makes it so that the field is tangential on a circle. Okay, of course, that's not a complete proof because you need to actually prove that this is the case. But that's the motivation, and that's the reason why it's natural to expect that something like that will be true. So this is essentially the unique black box that will remain, and I will prove something similar in the case of the caudal essay. Okay, so that was the second step. What happens for very small time? So step 3. Step 3 is essentially the same as step 2, but instead of looking at time 0, you look at time t. So you look at times t and t plus epsilon. So the picture is still on the board over there, but I will redo it because I want to tell you a few things as I draw it. So this is the disk. This is the curve up to time t. And this is the curve up to time t plus epsilon. And epsilon will be very small. So I map this by gt, and I get the unit disk again. This red part is mapped somewhere here. Gamma t is mapped somewhere here, gt of gamma t. And okay. And what happens between times t and t plus epsilon is mapped somewhere here. Okay, and then there was this map gt t plus epsilon that finished the job of removing the whole curve up to time t plus epsilon. And that was doing something like that, like this, and the rest is red here, and the rest is red here. And there is somewhere here gt plus epsilon of gamma t plus epsilon. Okay, so if you look, and of course this here, this map here is gt plus epsilon. So again, we want to see what happens between times t and t plus epsilon. So we want to look at gt plus epsilon of z minus gt of z. We want to look at something like this, like the time derivative, but at time t instead of time 0. What we know is what happens for very small time. So what we know is essentially the behavior of this map here. So from step 2, what we have is that the limit as epsilon goes to 0 of gt t plus epsilon of z minus z over epsilon is something. It's something which is not exactly this, because instead of growing from 1, here the slit is removed at 1, and here the slit is removed at a point which is gt of gamma t. So to obtain something similar to this, you need to rotate the picture to map this back to 0, well, to 1, and then apply what you have from step 2. And as it turns out, what you get like this, so you need to rotate, you apply this, and you rotate back. What you get is very similar to this, but instead of having a pole at 1, you just have a pole at gt of gamma t. So what you get is that this limit is equal to, well, z times gt of gamma t plus z over gt of gamma t minus z. So this is what you get as a derivative in epsilon of this guy. So it tells you that the derivative in epsilon at epsilon equal to 0 of gt t plus epsilon is equal to this. But gt t plus epsilon is just a composition of this guy and that guy. So it's gt plus epsilon composed with gt minus 1 at z, and this is equal to z times gt of gamma t plus z over gt of gamma t minus z. Okay, so that was exactly the same as step 2, and now what I want is the derivative of this guy here. So I will just write that gt plus epsilon is this gt plus epsilon composed with gt minus 1 composed with gt, and I differentiate in epsilon. I apply the chain rule, and all it does is that it composes on the right by gt, because there is no dependency in epsilon here. So all it does is that you get this composed with gt on the right, and so it replaces every z here by a gt of z. And what you get is that d over gt of z is simply equal to gt of z times, okay, this was wrong, this, oh, that's good, gt of gamma t minus gt of z plus gt of z, sorry, divided by gt of gamma t minus gt of z. Okay, so it's very boring to write gt of gamma t constantly, and I will use a shorter notation. Notice that gt of gamma t is on the boundary, so I will define beta t in such a way that gt of gamma t is the exponential of I times beta t. And that will be the final version of the equation. So far we have this equation here. So the key remark now is that gt of gamma t is a continuous function of t. That's a consequence of this, that gt depends continuously on t, gamma t as well, and by composition, gt of gamma t is a continuous function. So it's a continuous function on the circle. What you can do is to lift it by the exponential, and what you get is that there is a continuous function beta t such that for all t, the exponential of I times beta t is equal to this point on the boundary. This is not what I'm supposed to do, I guess, but so in other words, this will be the real valued function I was looking for at the beginning, which encoded the curve itself. Just by topology, you can find the continuous function beta, which is real valued and which tells you about this boundary point, this moving boundary point. So here is the second, so this is step 4. So the map from t to gt of gamma t is continuous. And so there is a function beta t, t positive, which is continuous and goes from r plus to r, such that for every t, gt of gamma t is equal to e to the I beta t. So of course the existence of beta t is trivial. The fact that it's continuous is something that needs to be checked, that you can make a continuous determination of the argument of gt of gamma t. But you can do that because you start with a continuous curve and you have a continuous family of conformal maps. Okay, and so if you plug this into this equation, what you get at the end of the story is the following: that if you start with a continuous curve in the disk, and if you parameterize it like this, according to the conformal radius at 0, And if then you look at GT, which is a family of conformal maps, removing gamma up to tan t, then this sequence of conformal maps satisfies a PDE, which is that d over dt of gt of z is equal to gt of z times e to the I beta t plus gt of z divided by e to the I beta t minus gt of z. So this is the main equation. This is called Loevner's equation. And if you have to remember one formula for the course of today, it's this one. Yes? But this is a differential in epsilon. And what you compose on the inside does not depend on epsilon. So there's no missing term. It's just a change of coordinates that you use from here. That's what you get from the time parameter, that the only dependency in epsilon is here. Okay, so this is called Loevner's equation. And so at the end of the day, what you get is that you started from gamma, which was a curve. And we did all this fancy construction, and the end product was two things. Was this function beta and the equation L. So we started from a curve, and we obtained one real-valued function, real-valued continuous function, and one differential equation, which really is not part of the information. It's just the way you encode something into beta. So it's probably should be more like here. Okay, so that was the plan. We had a geometric object, and we wanted to encode it using a continuous function. So this will play the same role as the contour function for a tree or something like that. Okay, so the key remark now is that no information was lost. So it's really a coding of the curve by something which is much simpler, because it's real valued as opposed to complex valued. So why is that the case? Because you can go backwards. You can start from beta. You look at this differential equation, and you can solve it. Solve L. So when I say it's a PDE, in fact, it's not exactly a PDE. It's just the flow of an ordinary differential equation. There is no differential in Z in the picture. All you do is that you follow the flow of this equation from different starting points. So you solve L. You need to say something about the initial condition. And I said it in passing, but the initial condition is that at time 0, you remove nothing from the domain. So GT is the unique map mapping the disk to itself with the right normalization. And that's exactly the identity. So you solve this equation starting from G0 of Z equal to Z. And by this I mean that for every point Z in the disk, this is an ordinary differential equation which you can solve. So you cannot solve it for all times. So for every Z, there will be some tau Z such that the interval between 0 and tau z is the maximal interval on which you can solve the equation. That's given by the Cauchy-Lipschitz theorem, that such that L from Z has a solution on 0 tau Z and not further. So it's the explosion time. If you look at the equation, it has a singularity, and you reach the singularity when gt of z becomes equal to e to the I beta t. And when you reach this, then the equation becomes singular and you cannot solve it anymore. And this occurs at some time which depends on tau z. Okay. So there is, once you have this tau z which depends on z, what you get is you can look at what happens at fixed time t. Yes? Yes, but this was not information because we identified curves up to time reparameterization. So it was lost yesterday. It was not lost today, if you wish. It's information that you don't care about, so it's okay to lose it. It was lost yesterday. Yes. Yes, that's where the information is going. Nothing has disappeared, but this aspect you don't care about, so you can forget about it. Yes? The thing is, as if you solve this for gt of z from fixed z, gt of z will approach the boundary sometimes. Maybe it's clearer if I do a picture. So here is an example, and that's exactly where I'm coming to. That you, okay, maybe I'll do a picture and then I'll answer everything simultaneously. So example, what happens is if beta t is equal to 0 for all times. So what it means is that you are solving dt of y is y times 1 plus y over 1 minus y from y, which is the point z, which is what you want to do. So if you start here, you are following exactly the vector field that I was drawing before. So the trajectory is like this and converges to minus 1. And at minus 1, this becomes 0. So every point that is not on this interval will end up arriving at minus 1. But if you start on this interval, well, the flow goes to the right, and the modulus of the vector field is bounded below. So eventually, you will reach the boundary. So what it says is that if you look at the solution at time t, the solution is well defined in the complement of the set of the points from which you reach here before time t. So that's exactly what happens if you solve this. Well, kt, you can define kt, which is the set of z such that tau z is less than t. So it's the set of points from which you explode before time t. And you can look at ut, which is u minus kt. So you have this differential equation. You can solve it from every z to some time. And if you want to look at time t, well, you can solve it in some subdomain, but not all of the disk. So there is this kt, which is the set of points from which you explode before time t. But the remark is, so if you are in this framework, so if tau z is less than t, then what you get is that as s approaches tau z, as s increases to tau z, So as you approach the explosion time, what you have is that for the solution not to exist anymore, this has to blow up. So what you have is that e to the I beta s minus gs of z, this goes to 0. This is the only way you can have a solution that is not defined. You have to reach the singularity. And so what it tells you is that now as s goes to tau z, what you get is that e to the I beta sub tau z, which is perfectly well defined, that's equal to g tau z of z. That's what you get in the limit. It's not differentiable, but it's still a continuous family of conformal maps. So you can let t go to tau z and you get something in the limit. But remember that this here, e to the I times beta tau z, that's the same as, so it's written here, is the same as g tau z of gamma tau z. So this, on the other hand, is equal to g tau z of gamma tau z. And g tau z is a bijection up to the boundary. So really what you get here from this equation is that z is equal to gamma at tau z. So what you get from this is that the set of points at which you explode, the set of points from which you cannot solve the equation for all times, is exactly the set of points that were on the curve. And from this you get also that, in fact, kt here, let me call it kt tilde because we don't know yet that it's the same as kt. So what you get is that the set of points for which this is true is the set of points that are on the curve at a time which is less than t. And so what you get is that, in fact, this is the same as gamma between 0 and t, which is what I was calling kt. So this is what I mean by no information is lost. If you solve this equation and you define k tilde t, which is the set of points at which you cannot solve it all the way to time t, then kt is exactly the same as the curve up to time t. So you can recover the curve from the equation just by looking at when you cannot solve it. So that was the contract. We had to encode a curve as a function. And this is somehow the inverse bijection. That if you start with a function, you get everything you needed. Okay, so I have been cheating a little bit. Not in what I wrote, but in what I said here. All I said was true, but it was hiding a little bit of the truth. So it is true, and I essentially proved it, that if you start with a curve gamma in the disk, and you write Loevner's equation, then you can encode it as beta. And it is true that in this framework, if you start from beta and you do this on the right, you get gamma back from the equation. So this sounds very smooth and very bijective, but in fact it's not, because there is some information on beta. So beta cannot be really anything. And what we want to do now is to forget that there was a curve before and try to do the construction backwards. You start from beta and you want to solve the equation, but for an arbitrary beta. So you don't know in advance that beta comes from the description of a simple curve. And the question is, can something go wrong if you do it for an arbitrary beta? And the answer is, of course, if I ask the question, the answer is yes. Something can go wrong. And you can have pathologies that appear if you're not very careful. So that was the construction. You start with gamma, you get this equation. This construction going backwards works very well if you start it from a curve, but now start with any beta. So now start from any beta, which is a continuous function. Still has to be continuous because that's at least reasonable from what we started from. So you start from this and you define kt as before. So kt is the set of z such that tau z is at most equal to t. And ut is u minus kt. So you don't know that beta comes from a curve anymore, but you try to do the same construction as before. So you solve the equation. And so gt is the solution of L So what do you know about gt? Well, there is something more that I have not said when I was going backwards. If you look at the way this depends on z, or this depends on gt of z, you will see that this is a holomorphic function of gt of z. In other words, you are looking at an ordinary differential equation, you are following a vector field, but the way this vector field depends on space is holomorphic. And that implies that gt, which is the solution of L, is itself holomorphic. That's the general theory of differential equations. If you integrate a vector field that has some regularity, what you get by integration has the same regularity. So gt is automatically holomorphic. So what more can you say about gt? Well, the second thing is that gt is automatically one-to-one on the inside of the set where it's defined, so on ut. And in fact, this is proved at the same time as proving that gt is the unique conformal map from ut to u with the appropriate boundary, with the appropriate normalization. So normalized. So why is it normalized first? It is normalized because if you look at the behavior at 0, if you put z equal to 0 here, well, you will find that gt of 0 is always equal to 0 and the derivative is 0. So 0 is a fixed point. And then if you look at the derivative at 0, because g is equal to 0, this vanishes. And what you get is that the derivative at 0 is exponential of t. So you get exactly the right normalization just from the equation by letting z equal to 0 in the equation. So it's a holomorphic function on ut. Why is it one-to-one and why does it cover the whole of u? Well, that's just because you can look at the backwards flow. If you're looking for z such that gt of z is equal to w, so the argument, so the proof. So let w be a point in u, and we are looking for z in ut such that gt of z is equal to w. So what you do is you do it backwards. You are looking for z such that if you evolve this equation for time t, you land at w. Well, what you can do is you look at the backwards flow from t to 0. So you can look at the backwards flow. You can solve dt of ht of z equal to minus ht of z times e to the I beta t plus ht of z over e to the I So maybe this is wrong. D to the s of hs of z is minus hs of z times e to the beta t minus s minus hs of z over e to the I beta t minus s minus hs of z. So instead of going from time 0 to time t, you go from time t to time 0. And so you want to look at g sub t minus s somehow. That's why there is this beta t minus s. So now this is another equation, which is the backwards Löwner's equation. But now there is no singularity. Well, there is a singularity, but the vector field at the singularity is pointing inside the domain. So if you start inside U, this field points you back towards 0, so the solution is defined for all times. So the solution of this, Hs, is defined for all times. Well, as long as you know what to put here, so as long as you are still in 0t. Okay, and so if you solve it, you get that h sub t goes from U to something which is living inside the domain, so it's ht of U, which is a subset of U. Okay, and then, well, if you just look at ht of W, so you remember you want to look at z such that if you evolve forward for time t, you find W. But the natural way to find z is to start from W and move backwards for time t. And that's what you do. You flow backwards and you start from W. And then it's easy to check that, in fact, gt of ht of W is equal to W. So z equal to ht of W is okay. So you can't find z, you just flow backwards. And this gives you everything at once, that it is one-to-one, because if you start from different points, they cannot land at the same time, because necessarily the only starting point is ht of W, and ht is well defined all the time. So you get everything at once. You get that gt is the unique map from ut to u. Okay. So far we get most of the same situation as before. We get this family of compact sets kt. We get a family of open sets which are their complements. And gt is normalized in the same way as before. What we don't get is that kt is obtained by a curve. So in fact, the classical classification of this is that we have three cases. So you can imagine three cases, and they turn out to be all non-empty. So case one is there is a curve gamma, a Jordan curve, such that kt is equal to gamma between 0 and t. So that's the case where kt, we say that kt is the curve. The curve. So this is what we started from, and this is one of the cases. And of course, if you start from any curve, you get one of these cases. And that was the construction before. So the second case that you can imagine is that there is a curve gamma, but it is not a Jordan curve. It's still continuous, and it generates kt in the sense that the following happens. So I will write it in the formula, and then I will make a picture, that kt is gamma between 0 and t tilde. So this tilde is the same as when I was speaking about the Brownian motion before. You look at gamma between 0 and t, and then you fill all the holes inside the curve, except the unique one that touches the boundary. So in the picture, you get something like this. So the curve will touch maybe itself. It will touch the boundary like this. So this would be gamma. So it should be red, but that should be gamma. And then kt is just what you get by filling all the holes like this. So this is gamma t, and this is kt. Okay, so this is the case. It's possible to obtain something like that. Well, just take this one and solve the equation, and I will give you the most general statement of Loewen's theorem just after that. But the third case, so here we say that k is generated by a curve. The third case is, well, just the complement, that there is no curve that generates kt. So this case is called pathological. And it's not very difficult to come up with a pathological case. So the kind of things you need to be thinking about for a pathological case is something like that. It's almost generated by a curve, but you introduce a singularity somewhere. So one way to do it is like this. Fix a disk inside the domain and construct kt like this. So you take a curve that will turn around the disk infinity many times. But notice that if you look at this from 0, the domain is very stable. It doesn't move very much. The boundary point is moving geometrically like crazy, but the domain itself is not shrinking by much because all you do is screened by the past. So in terms of the natural time parameter, this occurs very quickly. And there is the moment where you end up closing everything here and swallowing the disk at once. And this is a finite time, because at this moment it's still a simply connected domain. It has positive distance, so time has not gone to infinity in terms of the natural parameter. And then once you are here, then you exit, and then you go here. So this gives you a family of kt, and it turns out that you can encode it by beta t. And here beta t looks like this. So beta t is Hölder 1/2. There is one point t0 at which there is a singularity like square root of t minus t0 with a large constant. And so if you put beta to be this curve, this real valued function, what you get is this, and this is not generated by a curve because the curve would have to be simultaneously at all the points on the circle at time t0. So this is the kind of things that can occur, and of course they can occur at all scales at the same time, and they can do nasty stuff. So the situation is not as easy as it sounds. That you cannot always nicely solve the equation and obtain something that is geometrically nice. So I still have 4 minutes. So I have 2 minutes to give you the statement of Loewen's theorem in a general case, and 1 minute to give you a statement of one theorem telling you that there are cases when you can guarantee that you are in case 1. So I will start with the first one. So the first one, it's a theorem by Marshall and Roeder. It tells you that if beta is smooth enough, then you are in case 1. It's good to know because case 1 is the easiest one. It corresponds to many things that will come up in real life. So here is the theorem. Okay. Okay. So the theorem is, if beta is further 1/2 with a small enough norm, then we are in case 1. So this is Marshall and Rode. So there is a C0 such that for every function beta t, such that beta t minus beta s is smaller than C0 times t minus s to the power 1/2. So if beta is further with norm less than C0, further 1/2, then we're in case 1. So if you remember this is a Hölder function with a larger norm. So really Hölder 1/2 is the cusp across which things will behave differently. And you will see tomorrow when I speak about the caudal case and the Brownian scaling that 1/2 is very natural here. So this is a theorem that tells you that really Hölder 1/2 is the right scale. And just to spoil what I will tell you about tomorrow, turns out that SLE is obtained by taking beta to be a Brownian motion, and the Brownian motion is not Hölder 1/2. So this is useless in the case of Brownian motion, but nevertheless Brownian motion will be in one of the first two cases. So this will not occur for Brownian motion. And I will not have time to prove it, so you have to go to the course by Lauder in week 3. Yeah, to have proof of this and a lot more about Loevner chains. Okay, so I will just end by just the statement, the initial statement by Loevner about the existence of such a function beta and the existence of a family GT that encodes something geometric. So the theorem, like Loevner, says the following. So instead of starting with a curve, you want to look at a very general setup. So you start with KT, which is an increasing family, so T positive, of compact subsets of the closed unit disk. So far I was considering curves between 0 and T, but let's say you take any increasing family of compact sets. So you have GT that maps, okay, and let's say the 0 is not inside any of these. And GT is the map that maps U minus KT conformally back to U, such that GT of 0 is 0 and GT prime of 0 is positive. So that's the general framework. Instead of a curve, you have a family of compact sets. So then, and I will end by this, so there is beta t such that GT is solution of the Loevner's equation if and only if this family of compact sets is continuous. And continuous means, I will make a picture. So for all epsilon there is a delta such that for all t there is a cut set C such that kt plus delta is contained in kt union the cut set, and the cut set is small, is smaller than epsilon. So this probably makes no sense written like this, so I will make a picture. So what it tells you is that if you fix epsilon small, there is a delta such that between any times that are separated by less than delta, kt cannot grow very much. In the sense that So if this is kt, you can obtain kt plus delta by adding to kt something that is smaller than epsilon. So the typical case is like this. You move from kt to kt plus delta by adding something very small. So in fact, there is a tilde here, meaning that if this is kt, then kt plus delta is allowed to be this, where you fill this bubble. All this tells you is that the size of the opening here, so the size of the thing you need to add here is less than epsilon. It doesn't tell you much about the difference between kt plus epsilon, kt plus delta and kt. All it tells you is that whatever is in the complement here can be separated from 0 by adding something that is very small. So in the case of a curve, it's exactly saying that the curve is continuous. But in this case of the spiral around the circle, this is satisfied because as soon as you are deep enough, well, you can add the whole disk here by adding the very small shortcut, crosscut at the opening of the spiral. So this is the right notion of continuity, and this is the right framework for looking at Leuven chains. Okay, I think I overshot by a little bit, but not too much. But I really wanted to state this because I think it's a very nice theorem.
You hit this last few phrases written on the
Here? So there is beta such that GT is solution of Leuven's equation if and only if the family of KT is continuous in this sense that you can go from KT to KT plus delta by adding something smaller than delta, than epsilon. Yes? Well, no, because, okay, yes, yes. Sorry. This says enough about K0. This says that G0 has derivative 1, so by the Schwarz theorem, it has to be the identity. So maybe, yeah, I was not careful enough. G0 is the identity and K0 is empty. You're right. Thanks. K0 is empty.
So where do you see that U minus KT is simply connected?
Okay.
Because there was a conformal method of this.
Because there was a twiddle here.
No, but on the other side of the economia.
Yeah, because there's a twiddle here. I define ut to be the simply connected component of 0 or yeah of simply connected complement, if you wish. Yeah, I was not very careful about the first two lines of the theorem because the important one is the last one. This notion of continuity by adding something, some very small crosscut. It has to do with the character-orderly convergence, yes. But it's not exactly the same. No, it's not the same because the disk of radius 1 minus epsilon converges to the disk of radius 1 under character-orderly. But this growth is not local. So this implies character-orderly continuity, but it's stronger. It really says that you add something that is local, not something that is very thin. Yes. Yeah. Well, what will happen is something like this. You have a disk, you have 0. What can happen is that KT does this. But at this time, KT becomes everything outside here. And that's fine. You don't need to keep any part of the initial boundary. And this is part of this twiddle construction or the assumption that you have a simple.
For any function g, we have one of the intakes where the thing lives to the limit.
Yeah. Okay. Well, thanks. See you tomorrow.